Okay, this is Professor Thompson. I'm going to do some examples from 5.1. The first one I'm going to do here is 9 in the book. So this is about a runner whose speed is increasing during the first 3 seconds of the race. And her speed at half-second intervals is given here. And I want to find the lower and upper estimates for the distance she traveled during these few seconds. So I'm trying to figure out distance and about speed. And so this is basically what we talked about in class, where when you think about the equation d equals rt, we've got the rate and we've got the time. You multiply those to get distance, and basically what you're doing is you're multiplying the area of a rectangle. The r and the t are the length and the width. So let's start making a chart here on the next page, and then we will emphasize that again. Okay, so what you can see here is what I've done is I've put the axis basically on the bottom left corner of the screen, and I've somewhat haphazardly put some dots that plot the points. So the scale across the right is time, and that is every 0.5 seconds. So each box has a width of 0.5 seconds. And then the top here, or the y-axis here, is velocity in feet per second. And this is in units of 1. So that means that every box has a height of 1 foot per second. So I had to do that to fit the scale. And so this is going to make some sort of graph. I can connect the dots, but what I want to do is I want to get an upper estimate and a lower estimate as good as I can for how far she went. So let's do right-hand sums first. So if you look at the interval from 0 to 0.5, let's make a square here. So let me get the other tool here. So I made this square, and I want to fill it in, basically. I want to say, I want the area of this rectangle, because what is the area of that rectangle? That area, right there. So I'll have to erase that arrow in a minute, but let's see. Its width is 0.5 seconds, and its height, I used the first point, it's 6.2 feet per second. So if I multiply those, that's basically 3.1, the seconds cancel, and I get feet. So if you think about, if I go 6.2 feet per second for half a second, how far do I go? Well, I go half that amount, right? I go 3.1 feet. That is exactly the same as the area of this rectangle. So to get the total change from the rate of change, because velocity is the rate of change of position with respect to time, to get the total change, I just find the area. So again, to get the total change, you just take the area under the curve of rate of change. And so if we keep going here, we're going to get the area of this rectangle. And I'm going to keep doing these right-hand sums. So let's fill in the rest of the boxes here. Alright, so you'll have to forgive my uneven tops of my rectangles. But anyway, if I want to get the total here, well, we already found the first rectangle was 3.1 feet. So let's keep going here. So that was 0.5 times 6.2. And that was 3.1. Then we want to add, well, the width was 0.5 every time. What was the next? Speed was 10.8, and so that gives us 5.4. And then the next rectangle we use 14.9. So that'd be 7.45. And then we had 18.1. So that's 9.05. And then we had 19.4. And that would give us 9.7. And then lastly, we use 20.2. That's 10.1. So now I just add all these numbers. And here we get 44.8 feet. And so that is the upper estimate because I use the right-hand sums, right? So because that's not necessarily related to right hand, but because it was an increasing function, if I was actually going to connect those dots, let's try to connect them with a continuous function here. See how the sums are going over the graph, and so that's an upper estimate. The other thing I could do is I could use, well, let me write that a little better. I shouldn't cross back over the axis. The other thing I could do is I could use a left-hand sum. So in that case, I would basically do the same thing, but I'd be using the left-hand endpoints here. So those would be the tops of my rectangles, right? And then 0 here. And they would look like this. Maybe I shouldn't use such a thick pen, but that's okay. I'd be looking at this area. And so in this situation, I'm using a lot of the same endpoints, but I'm using them as the left side of the interval. That looks awful. So anyway, so instead of using 20.2, basically the way you can think about this is, I would use all the same data, they would just tick down one, and so at the beginning, for the first one, I would have 0.5 times the height of the first rectangle, which is 0. So that's 0. So then the value I get is 34.7 feet. So those are my upper and my lower bounds, and that's the best I can get with the data that I have. So like we've talked about before, if they took more and more data, if they had it every quarter of a second, then you would get an even better estimate. And then if somehow they could actually record her instantaneous speed at each time, and you found the area of that using this idea of integrals, then we would get the exact total distance run just from the speed. Okay, so that concludes this problem. And yes, if you're wondering, I'm home for the weekend, and that was my mother yelling at me.